Hello, so now we go further to test of one sample mean in case we don't know the population variance. So previously we have seen what happens if we know the population variance sigma square. Now we are going to see what we will do if we don't know the value of sigma square or the population variance. In fact, we are going to use the same methodologies, only we have two significant changes. So we don't know the sigma square or the population variance. So instead we are going to substitute by the sample variance, which is S square. So to do this step, we have another step. Previously we have used the normal distribution or Z. Now we are going, instead of using the normal distribution, we are going to use student T distribution T. Or for simplicity, we call this as T distribution. Previously we have seen Z alpha, so alpha the same in the normal distribution or the T distribution. But here we have also n minus 1, which is also the degree of freedom. Now before going to test our hypothesis, let's recall what is the sample mean and the sample variance. We have a sample of size n, we have the sample mean as x bar, we have the sample variance s square. Previously we have seen the x bar, which is the summation of all elements divided by number of elements in the sample. We have seen that the sample variance can be calculated simply using this equation. Here we square each element, here we have the summation of all elements, after that square divided by n, and we divide all by n minus 1. Let's have a look for the student or T distribution. So the student T distribution is symmetric around the 0, the same as the normal distribution. Previously in the normal distribution we have identified the Z value, Z alpha, using only the alpha, which is the alpha here is the area under the curve from this critical point until positive infinity to the right, so to the right of the point. But here T, alpha and V is identified using the value of alpha and V. V is the same as n minus 1 or the degree of freedom. So we have the degree of freedom to be V or n minus 1, where n is the sample size. So alpha, as we have said, is the area under the curve to the right of T. We have a note here that if the number of elements in the sample or the sample size is very large, for example larger than 30, so the T distribution approximately will be like a normal distribution, and later we will have an example for this case. So now the test statistic is approximately the same like that we have seen previously in the normal distribution. But so now we have the null hypothesis as mu equal to mu naught. So instead of using Z naught as a test statistic, we are going to use T naught as a symbol. Instead of using sigma, we are going to use S, which is the sample standard deviation, because we don't know the population standard deviation. So our test statistic is the same, T naught. We have the difference between the sample mean and the hypothesized population mean. And after that we divide by the standard deviation divided by square root of n. Also we can have two cases. We can have the two-sided test if we have inequality in the alternative hypothesis. We can have one-sided test if we have larger than or less than in the alternative hypothesis. So now performing the test is exactly the same as we have seen in the case we know the population variance, but we are going to change every Z naught with T naught. So we are going to use the student or T distribution. Also we are going to use the sample standard deviation instead of sigma or instead of population standard deviation. So here we have the same for alternative hypothesis. Also the criteria to reject the null hypothesis exactly the same as we have seen in case we know the population variance. Also, for the p-value is exactly the same as we have seen previously in case we know the population variance, but instead of measuring the p-value using the normal distribution, we are going to use the t-distribution. Also, for the confidence interval are exactly the same as we have seen in the case we know the population variance. So if we don't know the population variance, we are going to substitute by sample standard deviation instead of sigma. Here we have the S, which is the sample standard deviation instead of sigma. Here we have S instead of sigma, which is the population variance. Because we don't know the population variance, here we have the S sample standard deviation. Here we have S sample standard deviation, always instead of sigma. Also, instead of Z alpha over 2, we have T alpha over 2, T alpha over 2. Here, instead of Z alpha, we have T alpha. Also, here we have T alpha. But additionally, here we have also the symbol V, which is the degree of freedom. Here we have V, the degree of freedom. Here we have the degree of freedom, because the T distribution always identified by alpha and degree of freedom V, which is the sample size n minus 1. So as we know, if the mu naught or the hypothesized mean does not belong to the confidence interval, we are going to reject the null hypothesis. Otherwise, or if the mu naught is included within the confidence interval, we are going to fail to reject the null hypothesis. So let's have an example. We have an example of the diode threshold voltage. So in fact, the diode is an important electronic device used in many devices and appliances. Maybe you have seen this diode, such as this is a special kind of diode, which is the light emitting diode, for example the green light or yellow or red. So an important property for the diode is the threshold voltage. For example, suppose the threshold voltage for this type of diode is considered to be 0.75 voltage. So now this is our initial assumption for this diode. So the threshold voltage in fact is the voltage where the diode start working. So now this is our population. We have taken a random sample of 10 elements or 10 diodes. So we have taken 10 elements. This is our sample and our sample size is 10. We have measured the threshold voltage for these elements or for these diodes, and these are the values. For example, we have seen 0.71 as a threshold voltage. We have seen some values as 0.74, 0.77. So this is our sample. Now our null hypothesis or initial assumption that the mean value for the threshold voltage to be 0.75. Now the alternative hypothesis is like H1, that the mean value does not equal to 0.75 because it is not tolerated that the threshold voltage to be higher or lower than 0.75. So we have a two-sided test because we are afraid the threshold voltage if have been changed into higher value or lower value. Now we are going to use the student T distribution to perform our test because we don't know the sigma square or the population variance. So we are going to substitute by the sample variance square or sample standard deviation S. So let's have the solution. Here we have the sample and here we have the reading or measurements. We start by computing or calculating the x bar, the sample mean. Summation of all elements divided by n, we have 0.738. We have the sample variance square in this equation we compute the sample standard deviation. We have 0.0358. We have the sample size to be 10, which is n. Now we compute the statistic T naught. So we have T naught is the difference between x bar minus and mu divided by s over square root of n. We calculate all these values to have T naught equals minus 1.06. So what are we going to do later? Now, so let's use 90% confidence interval. Previously we have used 95 confidence interval. Now let's have another confidence level or confidence interval as 90%. So we have alpha 1 minus 0.9 to be, so alpha we have 0.1. We have now the degree of freedom v n minus 1, so 10 minus 1 is 9, so degree of freedom is 9. So this is now the t distribution, which is symmetric around the 0. We have the acceptance region in the middle. This area, this white area, in fact is the same as confidence level, which is 90%. Now we have two-sided tests. We have alpha to be 10%, so we'll divide alpha into alpha over 2 to the right and alpha over 2 to the left. So we have 5% to the right and 5% to the left. So now our duty is to compute the critical values for t alpha over 2 and v and minus t alpha over 2 and v. So we can compute only one value, and this one is minus because the population or the curve is symmetric. Now we are going to use the t distribution table. So the t distribution table looks like this. Here we have the values of v or degrees of freedom, for example 1, 2, 3 until 10, 11, etc. And in the row here we have the values for alpha. Alpha is the area under the curve to the right of t naught, and here inside the table we have the values of t naught. So now we have alpha as 5%, so we are going to use this column, and we have the degree of freedom to be 9, which is 10 minus 1, so we have 9 degrees of freedom. So in the intersection we have the value of t alpha and alpha over 2 and v or n minus 1. So we have the value of t naught 1.833. So we have t alpha over 2 to be t 0.05 and 9 because alpha is 0.1. So we have this value in the intersection 1.833. Now we are going for the solution. So we have the critical values. Here we have 1.833 and minus 1.33. Now inside here is the acceptance region. We have t naught to be minus 1.05. So we found that the t naught or test statistic lies in the acceptance region or between the two critical values. So t naught lies between minus 1.833 and 1.833. This will lead us to fail to reject the null hypothesis. So finally we have found the conclusion to be we are going to reject the null hypothesis, which means that the average of the threshold voltage have stayed the same at 0.75 and has not changed to any lower or higher values.